Yes, please.
Eva, are you there? Leslie. So a piece of coin falls accidentally into a tank containing two immiscible liquids, A and B, as illustrated. There is a diagram to that effect. And the diagram is that we have two liquids that are immiscible within a container. This is liquid A and liquid B. We are told that the depth of liquid B is 8 centimeter. The depth of liquid A is 40. This is 40. And a coin I accidentally falls below it. So this is the coin. Now, calculate the displacement of the coin. Calculate the displacement of the coin when viewed vertically from above. The refractive index of A is 1.3. Refractive index of B is 1.4. Yes, this is the concept we went through under real depth and apparent depth. Okay. And refractive index, using this concept of real depth and apparent depth, is equal to real depth over apparent depth. That is when we view from above. Then we saw that the vertical displacement is equal to real depth minus apparent depth. The apparent depth. All right. So we went through this concept yesterday. I want to see how you can apply the concepts in solving this problem within 6 minutes, meaning 3 minutes for each. 5 minutes will do. Okay. Let's see how you can apply yesterday's knowledge to solve the question. Start with. You have all that you need to solve the question. A coin falls accidentally into a tank containing two immiscible liquids A and B, as illustrated in the figure above or below. Calculate the displacement of the coin when viewed vertically from above. Okay. Then if the refractive index of A is 1.3 and that of B is 1.4. All right, so start with. If you were not with us yesterday and you don't understand, and see if you got the right approach. So to determine the displacement, D certainly must be equal to the real depth, which is 48 centimeter minus the apparent depth, which is unknown. Meaning that to calculate for the displacement, we must determine the apparent depth and subtract it from the real depth. So the apparent depth for each of the liquids must be done one at a time. So since refractive index is R over A apparent depth of liquid A is equal to R on the refractive index of A. So this is giving me 40 divided by 1.3. This will be the apparent depth as viewed through A. Now, the apparent depth as viewed through B would also be equal to the real depth of B over the refractive index of B. So the real depth of B is 8. 8 on 1.4. And this is also, so the total apparent depth then, which is equal to A of A plus A of B. So we have 40 on 1.3 plus 8 on 1.4. Please sum this up for me. Sum up the total apparent depth for me. What will be the total apparent depth? Right, Mamiya, Rachel, and the rest of you, please get involved so that we can save time. Kelvin. I'm waiting. Oh, hurry up. What's the total apparent depth?
36.47.
That's the total.
I think so, yes.
36.47. Can somebody confirm it for us?
Please, I got 36.48.
Okay, let me also confirm. So 40 on 1.3 is 30.77 approximately. 30.77 plus then 8 on its refractive index, 8 on 1.4. This is also giving us 5.714. 5.714. Okay. So this plus, when we sum the two up, we have oh, hold on. So 30.770 plus 5.714, we have 36.48. Okay, approximately 36.48. So let's assume that it is equal to what Amma gave us. 30. I say Amma, Mamiya. 36.47. Usually, please, when you do these calculations and you have uh, long decimal values, please write your answers in 3dp. Okay, if you are shortening it or estimating it or approximating it, write it in 3dp. Therefore, the displacement. Hey, well, wait. The displacement will be equal to the total real depth, which is 48 minus 36.47. And what is 48 minus 36.47? What's the answer? Yes, a river. Like,
Mr. Edia, please, I think the approximation is a bit wrong. It's supposed to be 36.484.
no, what I'm saying is that, okay, I know it can vary, but when you are doing this, approximate your values in 3dp. So I'm leaving this in 3dp, this in 3dp. Then we sum that up, right? And you might get an answer close to this, right?
That's what I'm saying, that when you sum it up,
Frida, what is your answer? Correct answer here. Frida. Anawada. Weku, Kelvin, Jesse, Angel, Mamia, Rachel. Hey, nobody is talking. Rachel. Hey, I want to hear from you what you got as your correct answer. What is your correct take here? Let me hear from any one of you. A ray of light inside a rectangular glass block of refractive index root of 2 is incident on the glass air surface at an angle of 45 degrees. So over here we are told I is 45 degrees. If the index of refraction of air or refractive index of air is 1, under this condition, the ray A will emerge into the air without deviation. B will be reflected back into the glass. C will be absorbed. And D will emerge into the air with an angle of refraction of 90 degrees. Please, what is your take? Share your answers with me. Au revoir.
yes, please.
What's your correct answer? Au revoir, what's your answer?
Mr. Edia, please, the C.
D is your option. Nana Kwame. Nana Kwame, what's your answer? Safo. Okay. If you are not sharing your answers, let's move on. We don't have time to. So, A, the first option says it will emerge into the air without deviation. That is not true. A is out because once the angle of incidence is not 90, it has to deviate. So once the angle of deviation is not 0 degree, when a ray of light is perpendicular to the surface, please, angle of incidence is 0. This is because, you see, we measure angle of incidence from the normal. So if the ray is just along the normal, it means the angle between the normal and the ray itself is 0. But that the ray will be perpendicular to the surface. Okay. So when I is 0, it means the ray is perpendicular to the surface. It is only under this condition that the ray will not be deviated. The ray will go without deviation. So once I is 45, the answer A is not correct. B will be reflected back into the glass. Yes, whenever B is not correct because whenever you incident light, okay, on a transparent material, what happens is that part of the incident light will be reflected and part will be refracted. Look at the experiment. I'm going to incident laser. Through it. When you incident a laser beam, okay, through the surface, part of it will be reflected and part of it will also be refracted. So it is not correct that the light will be reflected. It will be shed, partly will be reflected and part of it will also be refracted. So the answer B is also not correct. Then C will be absorbed. Will be absorbed is not correct because when you incident light, part of it will be refracted, part of it will be reflected. If you are saying it will be absorbed, it means the ray will be kept, the light will be kept in the medium. It will not show, okay, which is never true. And then D, it will emerge into the air with an angle of refraction of 90. Said the light will emerge into the air with an angle of refraction of 90. Let's see if that is correct. So once I is 45, and we are giving the refractive index to be root of 2. By applying Snell's law, the refractive index, which is sine of I on sine of R, this is the angle of refraction. We are being told that it will emerge, the light will emerge out of the air with an angle of refraction of 90. Okay. So if the refractive index is root 2, and we have sine of 45 divided by sine of R, it means we are to calculate for R. We are looking for angle of refraction. So sine R is equal to sine 45. Sine 45 is 1 over root of 2. 1 over root of 2. So we have 1 over root of 2 divided by root 2, which is equal to 1 root 2 times 1 root 2 as well. Okay. Or let's apply mathematics properly. Root 2 is equal, 1 over root 2 is root 2 on 2. So we have root 2 on 2. This is root 2. Root 2 on 2 divided by sine r. Therefore, sine r is equal to root 2 on 2 divided by root of 2. Help me find the value of r. Help me find the value of the angle r by simplifying this. So by simplifying this, help me determine the value of r. Oh no, this is 1 over 2.
His R is equal to 30 degrees.
R is equal to 30. No, R must be 90. R must be equal to 90. Let's see where the issue is. So, root 2 is equal to sine of this. So, sine of the angle of incidence is 45. This is unknown. Okay. So, when you make sine R the subject, we have sine R equal to root of 2 on 2, okay, divided by root of 2. And R is 30. Okay, then it means that if R is 30, then it means we have none of the options right. None of the options right. The book also made a mistake and then gave D as the correct option. D as the correct option. I'll look at it and then see where the issue is. So the light will emerge into the air with an angle of refraction of 90. So if we are getting this to be 30, then this will also be 30. If this is 30, then the light will never emerge with an angle of refraction of 30, no, or of 90. So it is none of the option is actually right. Okay. I'll check and then address it. So please, the rest of the questions, I'll select some of them to be given to you as an assignment so that we can move on to refraction of light in triangular prism as we started yesterday. Okay. Please, is there any question? If you have any question. Okay. So if there's no question, let's move on to what we were doing yesterday. Refraction of light in triangular prisms. So yesterday we saw that for triangular prism, light goes through double refraction. And I showed you a triangular prism. This is it. Okay. Triangular prisms have peculiar angles known as refracting angles or angle of the prism. Okay. So triangular prisms have unique angles A. So A, B, C. And it is A because of how I'm labeling it. So different prisms have this. Now, this has two refracting planes, AB and AC. Meaning, when you incident light at this side, it will go through deviation. Or when you incident it from this side, it will go through deviation at AB. It will also go through deviation at AC. So light undergoes double deviation in triangular prisms. Now, the special feature this has is that it has the ability to add deviation here and then the deviation here to form a larger value of deviation. And because of this unique feature, the triangular prism is used for separating the white light, or yes, visible light into 8 various components. So when light is incidented, if there's a normal to the side AB and you incident light at AB, it will deviate here. And when it is also emerging out of the prism, it will also deviate. Okay, so when you extend this and then extend this, you have a larger deviation. And it is for this reason that we use triangular prism for the dispersion of light. So unlike rectangular prism where light goes through a single deviation, if there's a normal and you incident light, it will deviate and then come out from the other end. But whatever pertains at AB, the same thing pertains at DC. So it is, the deviation is just similar to only one situation because whatever is here is equal to this. And that is why angle of incidence equals the angle of emergence E. But as for this, because they are not, these sides are not parallel, light will go through deviation here and will also go through deviation here to form a larger deviation. So let's go into triangular prisms properly and then look at whatever, okay, there are some important relations or formula which will help us do our calculations and all that. Okay, so we have this as the triangular prism. Refraction angle of the prism is A. We have this side B. We have this side C. So the refracting planes are A, AB, and AC. Okay. Let's draw the normal to both planes, AB and AC. So we have this to be N1, normal 1. Then another normal here, N2. Let's incident lights at one end. Please, the light to be incidented can come from this end or this end. The choice is yours. Either you incident light here and then it emerges from this end, or you do it here. So let's incident light at AB. This is the incident ray, meaning this is the angle of incidence I. Because the light is moving from air to glass, at the plane AB, it will deviate towards the normal. So it will deviate. Let me clear this before. It will deviate. So this becomes the refracted ray. And as the light comes out of the prism, then you draw the normal there. N2. Here, because it's from glass to air, it will deviate away from the normal. It will deviate away from the normal. So this becomes the angle of emergence. Now, we want to see how the ray, the part of the ray is deviated. If we extend the two normals, N1 and N2, we have this to be the first, the angle of refraction with regards to the plane AB. Then this side is also R2. R2 is the angle of refraction with regards to the side AC. Okay, so this is the first angle of refraction in connection with the plane AB, and then the second angle of refraction in connection with the side AC. We want to see how the ray is deviated. This ray, the incident ray originally is moving in this direction. Originally, it's moving here. The emergent ray originally is also moving in this direction. So the angle between the refracted ray and then the original part of the incident gives us the first angle of deviation, D1. That is deviation with respect to AB. And then the angle between the refracted ray and then the original part of the emergent ray also gives us the second deviation with regards to AC. So this is D2. So what you must note is that for a triangular prism, there is double refraction R1 and R2, and there is double deviation D1 and D2. Now we want to determine the value for each deviation D1 and D2 at both planes. For vertically opposite angle reason, we could see that I is equal to D1 plus R1. Vertical opposite angles are equal. Therefore, D1 is equal to I minus R1. So if you want to calculate for the angle of deviation with regards to AB, you subtract R1 from I.
Touch my leg before
I'm coming. I want to mute all. Now we also want to determine this deviation, D2. So by vertically opposite angles as well, E is equal to this. So
my head.
I muted. So by the same reason, E is equal to R2 plus D2. Therefore, D2 is equal to E minus R2. Okay, so we have expression for the first deviation and then the second deviation. All right. Okay, now this is a point O, E, a point F, and a point G. Please open your eyes. We are going to derive important relations. So when considering the quadrilateral, if we consider the quadrilateral O, OAGF, OAGF, OJF, OAJF. You see, once this is the normal, this angle is equal to 90. This angle is also equal to 90. This angle is also 90. So will be the angle from the normal to this. Okay. So if the angle between N1 and this is 90, then the angle between this and this is also 90. Okay. So 90 from the normal to the prism, 90, 90. But once OAFJ is a quadrilateral, if this is 90, this is 90, then we can also say that the angle here plus the angle here is also equal to 180, because the sum of angles in a quadrilateral must be equal to 360. So if these two, if this is 90, this is also 90, summing up to 180, then this plus this must also be equal to 180. So that it will add to this to give us 360. So angle A plus the angle J, angle OJF. The angle OJF must also sum up to be 180 degrees. Please, if you are okay with this relation, let me know. If you are not okay, let me know so as to explain more. Are you okay with the equation?
No, please.
No, please.
Look at something. We are considering the quadrilateral OAJF. And for every quadrilateral, the sum of angles in that must give us 360. So once this is the normal, the angle from the normal to the prism, to the plane AB, this is 90, right? The same thing, once this is another normal, the angle from here to this side is also 90. So when I add this to this, it's equal to 180. Meaning, when I add this angle to this angle, it must also sum up to 360. It must also sum up to 180, because the sum of angles in a quadrilateral must be equal to 360. So it is for this reason that if these two add up to be 180, then these two must also add up to be 180 as written here. Please, are we okay? Hello, are you okay?
Yes.
Yes, please.
So this plus this must add up to 180. Now, let's consider a triangle. And that is considering triangle OJF. OJF. Because the sum of angles in a triangle add up to be 180, it means one interior angle of OJF, R1 and R2. R1 plus R2 plus this angle plus angle OJF. This must also sum up to be 180 degrees. Our reason is that OJF is a triangle, and the interior angles are R1, R2, and this. So if you are summing all the interior angles, then it must also be equal to this. Now, what I want you to do is that from equation 1, make angle OJF the subject and substitute that into equation 2. Make the angle OJF the subject in 1 and substitute in equation 2 and simplify. Yes. Make angle OJF the subject in equation 1 and substitute that into equation 2. If you are done, please share with me what you had after the substitution. Yes, whoever is true. Therefore, what did you get after the substitution? Yes, Fina.
Mr. Dear,
Go ahead.
please, R1 plus R2 is equal to A.
Exactly. So, when you make O angle OJF made as a subject is equal to 180 minus A from equation 1. So R, if you substitute that into equation 2, you have R1 plus R2 plus, this is OGM, plus 180 minus A must be equal to 180. And this will reduce to 0 so that you have A is equal to R1 plus R2. Class, this is a very, very important formula in refraction of light in triangular prism. What does it mean? What it means is that, you see, I earlier said that different triangular prisms have different refraction angles or angle of prism, okay, labeled as A or whatever letter you use to represent it. Meaning that this angle of refracting angle or angle of the prism A is also equal to summing up the two angle of refraction, okay, at both planes AB and AC. Meaning, assuming I don't know the refracting angle of the prism, but I have R1 and R2. If I add R1 and R2, I must get this. Or, assuming I know A, assuming in a question, I know the value of the angle of the prism A and one of these, and I'm looking for the other. Knowing A, knowing the other, I can easily subtract to get the other one. So this is a very important equation in refraction of light in triangular prisms. When we finish and we are applying this to solving questions, you understand it so much. Please, is there any question or is there anything to explain before we move on? Please, the class is for all of us. If you are not clear with something, let me know and then explain one more time before we continue. So we have confirmed that the angle, the refraction angle or the angle of the prism is always equal to R1 plus R2. Okay, then let's move on. Now, when we consider another, we are going to consider another triangle. Let me write the first equation we derived somewhere. So we have established that the angle of the prism A is equal to R1 plus R2. So we are writing this in our concept book. When we consider another triangle, considering the triangle OEF or OFE. OEF. Okay. This triangle because this angle here is 90. This angle here is 90. It is like we'll have this size of the triangle being the same. So the side, this side and this side is the same. So it forms the triangle OEF is more or less like an isosceles triangle. And if you have an isosceles triangle, the sum of its interior angles must be equal to its external angle. And this is the external angle. So when we sum D1 and D2, it must be equal to this. So this angle, which we are representing as D total is equal to D1 plus D2. Due to the reason I told you that the sum of the interior angles of an isosceles triangle is equal to its external angle. Okay, you see earlier I told you that the unique feature, one of the unique features a triangular prism has is that deviation occurs at the two planes AB and AC. So when light is incidented, it will deviate. When it is coming out of it, it will also deviate. But triangular prisms have the ability to add deviations here and here to form a larger deviation. And that is what this spells out. That we are seeing that the total deviation over here is equal to the deviation D1 here and then the deviation D2 at the other side. Please, is that point understood? Hello, is that understood?
Yes, please.
Now, you see, we earlier had a relation for D1. D1 is equal to I minus R1. Then D2 is also equal to the angle of emergence minus R2. Let's substitute these two relations into the equation. We have D total being equal to I minus R1 plus E minus R2. We can group like terms. So I plus E minus R1 plus R2. You got this? This is minus. If you are
Mr.
factor, hello.
Please, I have a question. Please, in triangular prisms too, does the I equal the E? Like, is the I equal to the E
It
in
happens on
triangular?
conditions we will later talk about. It's not absolute that I is always equal to E, but it happens on condition, which we'll talk about. Is that
Okay. Yes.
so? Because we have minus R1 and minus R2, I'm pulling out negative, and within the bracket, I'll have R1 plus R2. So D total is equal to I plus E minus R1 plus R2 is equal to E. So in place of R1 plus R2, let's substitute E. This is another important relation to use in calculating for the total deviation. So if you are calculating for the total deviation within the prism, it is equal to D1 plus D2. But then when we expand it the total deviation is equal to I plus E. I is the angle of incidence. E is the angle of emergence minus the angle of the prism. That will also give you an expression for. So we have derived this, and then this. Very, very important relations in refraction of light in a triangular prism. Is there any question up to this stage? So please write them, take your time, write them. And then at your free time, you have to go over to master how these relations are derived. We are not done. Now, if you want to calculate for the refractive index, or if you want to determine the refractive index, as usual, Uncle Snell's law. So the refractive index of the glass block, which we are representing by nu, is always sine of the angle of incidence ratio to the sine of the angle of refraction. But the question is, which one? Because we have two refractions, R1 and R2. You can use any if the light is from left to right, meaning that it is incidented from here, okay, from left to right, then the angle of refraction will be equal to R1. And if the light is from right to left, okay, right to left, then the same refractive index can be calculated by taking sine of E, angle of emergence, okay, to the sine of the second angle of refraction, R2. So these are the two possible expressions you can use to calculate for the refractive index in triangular prism. And both must give you the same relation. Of course, we'll be solving questions. So you understand how this applies, okay, or how we apply this in solving problems. Now, supposing the angle of incidence is 0. Supposing I is 0. And if I is 0, I earlier explained that if the angle of incidence is 0, then the ray will be perpendicular to the plane AB. So in illustration, this is how I can illustrate it. This is the normal. Let me draw the normal very well. So if I is 0, then it means that the incident ray must be along the normal, meaning the normal and the incident ray are parallel. And parallel lines have an angle of 0 between them. Okay, so either for I to be 0, the incident ray must be along the normal, or it must be perpendicular to AB, meaning that the angle between the ray and the prism must be 90 degrees. So if the angle between the ray and the prism is 90, then it means that I is equal to 0. If I is 0, look at what will happen. The total deviation. Now, I earlier was telling you that when light hits a transparent medium and the incident light is perpendicular, what will happen is that the light will not, let me clear the diagram and redraw it well. For this illustration. This is a giant triangular prism. I have my normal here. If the incident ray is just along the normal, this is the normal, then it means I is equal to 0. Now what will happen is that because I is equal to 0, the light goes undeviated within the prism. So it will go through the prism undeviated. So when I is 0, R1 would also be 0. But we cannot say that R2 is 0. It will go undeviated within the prism. But then, when the light is emerging out of the prism, look at what will happen. This is the point of incidence. You see, to this plane AC, the light is not incidenting at AC perpendicularly. And so it will deviate. Here, it is going undeviated because the light is hitting AB perpendicularly. But to AC, it is not hitting, incidenting on it in that manner. And so there will be deviation when it is coming out of the prism. And how will it deviate? Because the light is moving from glass to air, it will deviate away from the normal. And so when you extend the path of the refracted ray backward, you will get the deviation, the angle of deviation. Okay, so yes, I is 0, but there will be R2. R2 is always the angle between the ray, the refracted ray, and the normal. So this will be R2. R1 will be 0, but R2 will not be 0. And this will be the deviation, D2. So if I is 0, we have the total deviation being equal to here I plus E minus A. So I is 0. So we'll only have E minus A. And don't forget, this is E. This is E. This is E. So we can find if I is 0, then the only deviation which will survive here will be D2. Okay, and D2 is what we are describing as the total deviation. It will be given by the angle of emergence minus the refraction angle of the prism. Okay, and don't forget, you also use A is equal to R1 plus R2 in solving your problems. Okay, so you pick, this is what I want you to understand if I is 0. Of course, I'll look for questions where we can apply so that you understand how to calculate for total deviation in such events. Please, is there any question? Is there any question on what I've discussed so far? Are people here? All right.
We are
Yes.
here.
Okay. Now let's look at the question you asked. It is not for refraction of light in rectangular prisms, always I is equal to E. But for triangular prisms, it's not like that all the time. It occurs on condition. So let's look at the minimum deviation. A condition of minimum deviation. From the total deviation, we've seen that it is equal to I plus E minus A. Meaning the total deviation in triangular prism, total deviation in a triangular prism depends on some factors. Depends on some factors. What are these factors? One, it depends on the angle of incidence. Angle of incidence, I. And that is obvious. From the equation, you could see I. Then it also depends on, let's talk about factors which we can see. The angle of the prism. Angle of the prism or the refracting angle. Refracting angle. Either you term this as the angle of the prism or refracting angle. So in questions, I'll be using, as for E, the angle of emergence, we won't talk about it because whatever the value of I would give a corresponding E. So when you change I, it will change E. So once we've talked about I, that's it. But there are other factors which you can see here. And these are the total deviation also depends on the refractive index. The refractive index of the material. Refractive index of material. Material used as a prism. Okay. Then finally, the factors on which the total deviation depends is the wavelength of the incident light. Wavelength of the incident light. Wavelength of the incident light, what I mean is that the color, you see, different colors of light have different wavelengths. So if you incident a blue light, its wavelength will be different. It will also affect, its wavelength is different. The refractive index of the material will also be different. Now it will also affect how the light is deviated. Don't forget information of in dispersion of light, where visible light or white light is incidented at one side of the prism, it will deviate towards the normal here. Then, as the ray comes out of the prism, it will further deviate. So when we extrapolate the line, incident ray, we'll have this. When we extrapolate this one, we'll have this. So this is D1, This is D2, and this angle is the total deviation, dt. Now, the white light will be divided into the various colors or components, which is red, followed by orange, yellow, green, blue, indigo, violet. Okay, so the total deviation is what spreads out the colors. The colors are spread over that angle of deviation. From this, we could see that red light is the least deviated. Then violet is the most deviated. Okay, so in the rainbow colors, red is the least deviated, whereas violet is the most deviated. What it means is that if you incident, and this is white light, which is no color, meaning if you pick one of them and you incident it here, blue and red, it will be deviated differently. Orange, green, and so on and so forth. So the total deviation is also influenced by the wavelength of the incident light. When you change the wavelength, the deviation would also change. So these are the factors on which the total deviation within the triangular prism depends on: one, the angle of incidence; two, the angle of the prism, the refracting angle of the prism; three, the refractive index of the material used as a prism, meaning if you use glass, the refractive index of glass is different from the refractive index of plastic, and so it will affect the deviation. Then four, the wavelength of the incident light. So take note of this. Okay. Now, once these are the factors which affect the extent of deviation, if we pick one of them, angle of incidence, if we pick the angle of incidence, there's a normal, and then we increase the angle of incidence gradually from whatever value, and then as we increase the angle of incidence, the angle of deviation, decreases. Here, the angle of deviation, I mean the total deviation within the prism. So as we increase the angle of incidence within the prism, the angle of deviation also decreases. So I'm going to create a table for you. You'll fill this and see it for yourself. So let's start I with 20, 30, 40, 50, 60, 70. Okay. Then 80, 90. And this is what I want you to do. You are going to fill this data. D1, determine D1. D2, then find, before D1, you find R1, R2, D1, D2, then we determine D total. We just want to prove what we are doing. So let me start one with you. We are given a prism whose refraction angle A is 60 degrees. Then this prism also has refractive index to be 1.5. We are to determine the first angle of refraction, second, then the first deviation, then calculate for the total deviation. So if I is 20, using Snell's law, sine I over sine R1. Okay, I think this will even help you in your calculations or how to apply the relation. So the refractive index is 1.5. We are beginning with an angle of incidence of 20. So sine of 20 degree over sine of R1. Please help me find R1. Erefua, Elizabeth and Co. Mamiya and Co. Please help me calculate for R1. Kelvin and the gentleman, I don't hear from you. What will be the value of R1? Just give me R1 in 1 dp.
Thirteen
Please,
point
13.2.
13.2.
13 point.
Okay. So if R1 is 13.2, what will be R2? How do we determine R2? Ideas. Before I come in. Mamiya, any idea? Rachel. Mamiya.
Subtract R1 from A.
Exactly. Exactly. Thank you. So, you see, because A is equal to R1 plus R2, once you have R1, you can easily find R2. A minus R1. So, 60 minus 13.2, which is okay. What she said is exactly what I'm doing. She's saying that once we have R1, we subtract R1 from A to get R2. Okay, Jesse, that's what she said. So please give me this in 1 dp. 60 minus 13.2.
46.8.
How do we calculate D1? Idea. How do we calculate D1? Eva, is your microphone damaged? Eva. Yes, Kelvin and Co, how do we determine D1? I'm
I
listening.
minus R1.
Hello, Eva. I was calling you. So you later.
Yes.
So you see,
Okay.
I is equal to I minus R. So once I say D is equal to I minus R. So once we are looking for D1, you must subtract R1 from I. Okay. So what's the value of D1? What's the value of D1?
6.8.
Oh, this is 6.8. What about D2? Okay, let me guide in determining the second deviation. You see, I was saying that you can find the refractive index by sine of I on sine of R1, which will also be the same as when you are moving from right to left, sine of E over sine of R2. So use this to find R2. As for R2, we even have it. Okay. Yes, we have R2 already. So you use the refractive index, and then the value of R2 to find for the angle of emergence. Now once you have the angle of emergence, then D2 is equal to E minus R2. So that's how to calculate for D2. Find the angle of emergence, okay, by using the refractive index and then R2. So if I should even substitute sine of, okay, you get me the value before. So help me calculate for the angle of emergence with regards to this angle. So you will complete this table so that we use it properly in our next meeting. Okay, so 1.5 is equal to sine of E. We are looking for E divided by sine of R2. R2 is 46.8. Therefore, sine of E is equal to 1.5 times sine 46.8. Please help me determine the value of E. What's the value of E?
1.093.
No, the value of E.
E.
Yes.
Okay.
The value of E. So meaning find sine for 46.8, multiply that by 1.5. Then take the sine inverse of whatever you have. Okay.
You get 0.019.
And then when you take the sine inverse,
That's the sine inverse.
let me go through it myself. Sine 46.8. This is equal to 0.7289, blah, 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 right? This times 1.5. Mamia, that is giving me 1.0906. And when you take the sine inverse of this, is giving you error. It is an error because we don't have to start from this value. We should have started from 30, 40 down, not from this. Okay. So all that I want you to do is that when we use 20, we cannot determine D2 because E will be, Mamia,
Please, why is there a math error because you started with the smallest number?
you see, some angles are not applicable. So in the laboratory, when we are doing this, the least angle we even begin with is somewhere 30, 40. Some angles are not directly applicable. Okay,
Yes, please.
or the next work you have to do is that check these values, how we got R1 and R2 and D. Especially, yes, once you, I think R1 and R2, check if they are correct, okay? Because I want you to finish the table. When you finish it, it will give us a trend, the trend of D total, okay? So the next angle to consider 30, 40, up to 80. 90 would also wouldn't give us anything because an angle of 90 means that if there's a normal, okay, if there's a normal, the angle of incidence, the light will just be along the boundary. The light will just be here because this must be 90. And if the light is just along this, it will not deviate. So the angle of 90 would also not work. Please, do you understand? Do you understand me? So this experiment is not applicable to all angles. So check from 20, check your values.
Yes.
Okay, and then end at 80. We can even end at 85. 85, but not 90. All right. So copy and then you will complete this table for me. But I want to talk about the theory so that when we meet next week, we'll compare whatever you got, okay, from the table to the theory. So as we increase the angle of incidence, the angle of minimum, the total deviation within the prism also decreases. So as I increases, D total decreases. You see it when you complete the table. Okay. Don't forget D total will be D1 plus D2. So whatever you get for D1, D2, when you add, it will give you this. And so you realize that as I increases, this one decreases. But it will decrease as you increase this, D total will decrease to a certain point. A certain angle of incidence would give you what we call as the minimum deviation or the least deviation. Why minimum or least? As we increase I, D total also decreases. But this decrease, let's assume this is 4.5. So as I increases, you realize this will be 4. I'm only creating values. Then 3.5, then 3. Now, at a particular angle of incidence, instead of D total to continue to decrease as we increase I, no. You realize that the trend will change. Instead of D to decrease, it will be increasing. 4. So as I increases, D will decrease only to a certain point. Okay, and then from there, though I is being increased, but it will be increasing. That point, let's assume that this is the point because it's reduced to the least value. So this is the minimum deviation. Now, at the minimum deviation, that is when you realize that the angle of incidence is equal to the angle of emergence. So at the minimum deviation, I is equal to E. Who asked this question? Somebody asked. Is that a referral?
Yes, please.
So a referral, you have the angle of incidence being equal to the angle of emergence only at the minimum deviation. Only at the minimum deviation. And don't forget that a particular angle of incidence would give you that. Now, apart from I being equal to E, you also see that at the minimum deviation, the incident ray passes through the prism, symmetrically. It's like dividing the prism into two equal parts. Okay, so I is equal to E on condition, not all this. Okay, at the attainment of the minimum deviation, then I will be equal to E. So if there's the normal, and then that particular angle is reached, then you see that this ray will divide the prism into two equal parts. And that's the only point where you see that I will be equal to E. So if I is equal to E, then at the same minimum deviation, you also realize that the first angle of refraction is equal to the second angle of refraction. So R1 would also be equal to R2. R1 would also be equal to R2. So at the minimum deviation, I is equal to E, R1 is equal to R2, meaning that they will not be different. I will not be different from E. So I is equal to E, and they are all equal to just I, angle of incidence. R1 is equal to R2, and they are all equal to one angle of refraction. Okay. Now, if this is what happens, then the earlier equations will change. The earlier formula or relations we derived would also change. How would they change? We saw that A is equal to R1 plus R2. Now, at the minimum deviation, you realize that I want you to help me. How do you think will be this relation? How will this relation change at the minimum deviation? If R1 is equal to R2 and they are equal to R, how will this change? Anybody to share what he or she sees with the house? If A is equal to R1 plus R2, how would this equation change at the minimum deviation? I'm waiting. I just a volunteer to just share. Chirame, can you help Kweku? Leslie, hey, Leslie, you are here and you also quiet. Rachel, Nana Safo, William. Oh, Frida.
Please, since R1 is equal to R2, so I represent R2 with R1, then it will be 2R1.
So either 2R1 or 2R2, but since R1 is not different from R2, the result will simply be 2R. Frida understood? Frida, are you okay?
Yes, please.
Because, you see, R1 is equal to R2. So, assuming R1 is 60 or R1 is 30, what will be the value of R2? If R1 is 30, what will be the value of R2? Quick.
30.
Therefore, A will be equal to 30 plus 30 because R1 and R2 are the same. 60. So, at the minimum deviation, A is just equal to 2 times the angle of refraction. Then, D total, which is I plus E minus A, would also change. This total will change because we have gotten to, under that condition, we have gotten to the least deviation, minimum. So T will change to minimum. How will this also change? I plus E. How will it change? Yes, just share your views. You can be right, you can be wrong. It's part of the game. How will this equation also change? Rachel, Eva, speak. Kweku. Yes, Frida.
2I.
Okay, Frida, let Kweku. Kweku, go ahead.
2I minus 2R.
Exactly. So either this is equal to 2I minus A, or you can also represent A by 2R. You are not wrong. But usually, we want to go by this. We want to go by this relation, the first one, to do something. We want to make I the subject from this. So we have I equal to the minimum deviation. I'm fond of using sigma to represent the minimum. Okay, let me be consistent. So D minimum plus A divided by 2. Now, you see, R is also equal to A on 2. Then we determine the refractive index of the material by using sine I on sine R. So the expression for the refractive index would also change at the minimum deviation. How will it change? At the minimum deviation, we have I to be this, R to be this too. Therefore, the refractive index would be equal to sine of I, which is now this, D minimum plus A all on 2 divided by the sine of R. R now is this, A over 2. So this is the equation to use in calculating for the refractive index of the material at the minimum deviation. But the value of the refractive index will not be different at the minimum deviation or without minimum deviation. The value must still be the same. All that we are saying is that we can use conditions that pertain at the minimum deviation to also calculate for the refractive index of the material. Please, any question? Any question? So please take note of this very well. Okay. So Frida,
Say,
under triangular prism, I is equal to A on conditions. The condition is that at the minimum deviation, it is only at the minimum deviation that I is equal to E. So questions pertaining to this will be specific, whether the situation is at the minimum deviation or without minimum deviation. It will be specific. So the question, based on how it is set, would inform the equation relations to use. We'll solve sample questions. So you certainly understand whatever goes into this. All right. Can I clean the board? Now let's look at a graph of total deviation against angle of incidence. A graph of total deviation against angle of incidence. Hey, Angel. Angel. Angel is gone. You go through the practicals of this at school. So we are plotting D total against, Mommy, are you there? Mommy,
Yes.
okay. So we are plotting a graph of D total against angle of incidence. So it's like dt is equal to I plus E minus A. Now we saw that as I increases, what happens to D? D total. As I increases, what happens to D total? Mami, I am Kofrida Elizabeth. As I increases, what happens to the total deviation?
decreases.
So when I is 0, it will give us the total deviation. When I is 0, meaning when the incident ray is just perpendicular to the refracting side, the refracting plane, we'll have the total deviation being equal to E minus A. So this will give us a maximum deviation when I is 0. When I is equal to a certain value, maybe 10, maybe whatever. So as we increase I, you will realize that this will be decreasing. when I is here. This will be decreasing. Then, at a particular angle of incidence, I deviation will reach its minimum value. Deviation will reach its minimum value. And then begin to increase as I increases. And then increase to the maximum again. So a graph of total deviation against I looks like this. And this point is equal to D minimum, the minimum deviation. So in your practicals, they'll ask you plot a graph of, okay, you go through this experiment. It's unfortunate you are not somewhere close. Other than that, I would have wished that we go through the practicals of this to get our values plots for this beautiful graph. But I'll still, in spite of the gap, okay, geographical gap, fill the table for me. We'll use it to plot this graph. Okay, so I value of 20, 30, look through it well and fill. We use your values to confirm this. So this is the graph of deviation. Okay, total deviation. Total because we are looking at DT, not a single D1 or D2. There's a graph of total deviation against angle of incidence. As I increases, D also decreases. And a particular angle of incidence would give us the least or minimum deviation within the prism. And from there, so this is the whole theory surrounding refraction of light in triangular prism. We'll go through question solving after we have seen, okay, you have completed the graph and then pick sample questions to go through. In fact, you get to understand better as you apply the concepts in solving problems. If you have individual questions to ask, please do so. Is there any question? All right. So if there is no question, this is where, as usual, we draw the curtains on today's meeting. Thanks for your presence, your contribution, your silence, and everything. We'll continue once again, probably next week. I'm here to look at our program to see when will be declared as break for Omega students. So until then, may the good Lord be with you. Take care of you. Take care of yourselves as well. And bye-bye. Your assignments, I'll forward them. So bye-bye to all of you. All right.
Bye.
Okay. If you are please, let me hear from you. Send me a message. I was about to forward an information to you, but